Hello students, in this video we'll solve a Lower Michigan math competition problem that is very similar to a locker key classical competition problem. Let's state it. It says, suppose we have subsets x1 through xk of the set of integers 1, 2, 3, all the way up to 2025. So this from, I'll just change the year number, won't change the problem at all. Right? You have a collection of subsets such that any 6 of them, and they're distinct. So these have to be distinct. They can't be the same. Any 6 of them unite to give, let's call this set, what should we call this set? Let's call this set over here S. Okay? Unite to give S. In other words, you pick any 6 you want, and you take their union, and you get S, okay? But if you unite any 5, you don't get S. Okay, so 6 will always give you S. 5 will always be short. Okay, 6 is all, 5 is short. What is the maximal number? K. Okay, I'm gonna find the largest K that works for this configuration, right? So let's figure out what's gonna happen over here. So here's the structure of this. It's a combinatorial proof, okay? So here's the idea. So let's let A be the collection of all groupings of 5 of x1 through xk. Okay? How many ways can you do this? There are k choose 5 ways to do this. Okay? Now here's the tricky part, okay? The tricky part is that now we can construct a mapping phi, which inputs a something from A, right? Takes something from A, right? And outputs something in S. And what does it do? It outputs the thing that was missed, because what's going to happen? If I give you something in A, it will output what's missed. Okay. This is injective, right? Phi is injective. Why so? Since 6 gives you everything, right? Since adding one other one gives you something else, right? So that means that if 2 of them output the same number over there, they wouldn't have been able to unite, because I could take those 5 and then you would unite those 2 and still miss something, which is a contradiction, right? So think like this. If it wasn't injective, I could find 2 groups of 5, right? That both missed the same thing, right? That came from the same thing that they missed. If that were the case, I could unite those 5 and those 5 and still miss something. But I know that 6, if you unite 6 or more, you're always going to get all of S. That's a contradiction. So phi is injective, since if phi of A, let's say phi A prime equals phi B prime, then A prime and B prime both miss the same number. But A prime union B prime is all of S, right? And that's a contradiction, okay? So that forces A prime to be B prime, right? And so A prime has to be B prime. Good. All right, excellent. And so now we're in good shape, because what does that tell me? That tells me, therefore, that this mapping is injective, right? So in other words, that tells me that the cardinality of phi of A is what? Is less than or equal to, it has to be at least what? It has to be at least this number over here. So the cardinality, so what can we say? We can say that k, choose 5, has to be less than or equal to, that's the cardinality over here, has to be less than or equal to the cardinality of that set over there, right? Because that's the cardinality over here, it's injective. So an injective function is going to map over there into S, right? And it's always going to be less than or equal to the overall dimension. If there's redundancy, then you have more, right? So it's less than or equal to this. And now, of course, here comes the sort of a hard part. The hard part of the problem now is that you basically just have to figure out, you have to do some numerical testing of this. And so the numerical testing is something that you can do quickly because you can test that the numbers what? So you're going to test numerically. To see that 14 choose 5, 14 choose 5 is 2022, and 15 choose 5 is 303. So k is less than or equal to what? K has to be less than or equal to at least 14, right? So k is less than 14. So k less than or equal to 14. 15 is too big. Okay? Now we can actually say that 14 will work. We claim that k equals 14 will work. Right? Why so? Now here's where the combinatorial things come in. Because 14, so 14 choose 5, is the same as 14 choose 9, right? Because I'm using the fact that n choose k is the same as n choose n minus k, right? That's exactly what we're using over here. So what do we do over here? So if we have 14, so what we can do is we can place the numbers 1 up to 2022, which was what this thing is equal to, right? These are equal to 2002, I think, right? 2002? Yeah, 2002. Into 9 evenly into 9 of the sets. Into 9 of the sets what? Into 9 of the sets x1 through x9, where no two have any agreement, right? Okay, good. Okay. And then we're going to place what? Place 2023 up to 2025 into all of the rest of the sets. Into all sets x1 through x14, right? And if we do this, what's going to happen? So now all of these things are everywhere, right? So if I pick any 6 of them over here, that's the same over here since there's a 5, right? I will always get what? I will always get that those things are in the right configuration. They're all in the right space because 9 and 5 have the same combinatorial structure over here. So that will be a configuration that works. Thank you very much.